When you allocate memory on the CPU side, that memory is pageable, meaning that operating systems can actually swap this memory to disk, and it's possible to allocate memory differently so that it's pinned. And this is something that users of managed languages, for example, .NET developers, do when they want to interop with the native side, because pinning memory allows you to effectively take its address and pass it somewhere while having a guarantee that the memory doesn't get relocated while you're using it. And in the context of GPUs, pinned memory has a performance advantage when copying data to and from the GPU. And in actual fact, even when you don't use pinned memory explicitly, CUDA uses it behind the scenes. So whatever happens, you end up paying for double for that copy operation. And the way to avoid it is to allocate memory using a special CUDA function called CUDA host alloc. So this is something you would use instead of calling malloc or instead of calling new to actually allocate memory on the CPU rather than the GPU. And this function allocates pinned memory and thereby accelerates this process of copying to and from the device. Correspondingly, you would use CUDA free host instead of delete to deallocate the memory that you've allocated. And the advantages are performance. The obvious disadvantage of pinned memory is that it cannot be swapped out to disk. So this puts some limitations on what you can do, because initially you must have enough memory to allocate, and you should also be deallocating it proactively in the sense of not waiting maybe until the end of the program for this kind of memory to be deallocated, but rather doing it as soon as you're done with it. So this kind of memory is great, but I wouldn't do a search and replace on all your projects, replacing, your allocations with CUDA host alloc, because it makes sense for those operations where you need to copy something to and from the device. And in fact, when you're using streams, it is a must. You have to use pinned memory, but it doesn't mean that it's a silver bullet because of the disadvantages I've just listed. So let's actually use our knowledge of CUDA events to try and measure the speed up that pinned memory brings to the table. All right, so let's try actually comparing the performance of memory operations using pinned memory compared to ordinary memory, shall we say. So I'm going to call this project pinned memory. All right, as is customary, I'm wiping out everything there is. And let's get typing. All right, so I want IOStream, and I don't think I want anything else. So what are we going to do? Well, I'm going to have this function called time memory. And it's going to time either pinned memory or non-pinned memory. So we're going to have a flag for whether it's pinned or not. And we're going to have another flag, another bool, for whether we're copying to device or from device. So I'm going to call it to device. There we go. All right, so what are we going to do? Well, we're going to have an array of a particular size. So let's do constant count. Let's say 2 to the power of 20. And I'm going to do it several times. So we're going to iterate the copy operation several times. Const int iterations, let's say 2 to the power of 6. And then the size, so the size of the memory is going to be count times size of int. All right, so we're going to use events as always. So CUDA event underscore t for start and end. And then we need memory for the host and the device side. So int pointers for h and d. We're going to have an elapsed value that we're going to calculate later on. And let's also have CUDA error underscore t for status, just in case. All right, so what are we going to do? Well, let's start timing the thing. So CUDA event create, well, at least create the events. So the start event and the end event. Then we're going to CUDA malloc, so allocate the device memory. That's going to be size. And then depending on whether we want memory pinned or not, we're going to do different allocations. So if the memory is pinned, then we need to use this special function. We need to use CUDA host alloc. And that's going to go into h size CUDA host alloc default. There we go. Otherwise we can just say h equals new int count, like so. Or we could have used malloc in this one. It doesn't really matter. Okay, so let's start recording. CUDA event record start. And then we're going to do those iterations. So here comes the loop with I going from 0 to iterations. And inside the loop, we're going to say that if this is going to device, then we're going to say status equals CUDA memcpy to device from host size CUDA memcpy host to device. There we go. Otherwise, it's the other way around. So status equals CUDA memcpy hd size CUDA memcpy device to host. There we go. I think this is correct. All right, so we're done with the iterations. Now we do CUDA event record. So record the event, and we synchronize CUDA event sync on the event. We calculate the elapsed time. So CUDA event elapsed time for elapsed start end. There we go. We've done the timings. Now we need to actually release the memory, which also is done differently depending on how you allocate it. So if it was pinned, then you would do CUDA free host. Otherwise, well, fairly obvious stuff. All right, then we free up the device memory, destroy the event, destroy the end event as well, and we return the amount of milliseconds that's elapsed. All right, so that's our timing function, and now we need to call it 4 times because we want to call it to device and from device, and we also want to try paged memory and pinned memory. So int main and cout, so let's say from device paged memory. I'm actually going to copy these from from something I made earlier simply because it will take too much time to type. So here we go. All right, so we're done. Let's run this. All right, and the results are in. So what you can see here is from device using paged memory took 149, and from device using pinned memory it took 90. And to device from paged memory took 179, and to device in pinned memory took 106. So it's not exactly a twofold improvement, but it's fairly close, I would say 1.6, 1.7. So hopefully this clearly demonstrates the fact that pinned memory is faster when paged memory when performing those copy operations.